On January 19, 2006, New Horizons launched as the fastest object ever built by humanity, tearing away from Earth at 36,000 miles per hour. After a 9.5-year journey covering 3 billion miles, it screamed past Pluto at 31,000 miles per hour, capturing data for just 22 minutes during closest approach. But here is the paradox: despite flying past a frozen world in the outer dark with cameras exposed for mere seconds, we discovered nitrogen ice tsunamis, glacial waves the size of mountain ranges that flow and churn like a lava lamp, erasing the surface in geologic real-time. How is it possible to detect active planetary geology on a world that should be frozen dead, using instruments powered by less electricity than a toaster? And with the nuclear battery failing, how much longer will we be able to analyze the nightmare unfolding on this frozen world? To understand the PLUTO flyby revelation, you have to grasp a counterintuitive detail about mission timing. When New Horizons launched in 2006, Pluto was still officially the 9th planet. By the time the probe woke from hibernation to begin its approach in 2015, Pluto had been demoted to dwarf planet. The mission left Earth aimed at a king and arrived at an exile. The original mission was simple: perform the first-ever reconnaissance of the Pluto-Charon system. But success required a special circumstance: a rare planetary alignment. The spacecraft couldn't carry enough fuel to slow down or speed up on its own. It relied on a gravity assist from Jupiter in 2007, stealing 9,000 miles per hour of momentum from the gas giant and cutting years off the travel time. This gravitational slingshot enabled 5 key discoveries that shattered expectations. First, Sputnik Planitia, the heart, a 600-mile-wide plain of churning nitrogen ice, geologically alive. Second, ice tsunamis, glacial flow patterns showing convection cells that overturn every 500,000 years, cosmic seconds. Third, Right Mons, a suspected cryovolcano 90 miles wide, spewing ice slush instead of lava. Fourth, the Blue Halo, a thin nitrogen atmosphere with blue twilight hazes, proving weather systems exist. And fifth, the Blade Terrain, jagged methane ice mountains taller than the Rockies, carved by sublimation. There is a stark divergence between what we expected Pluto to be and what it actually is. The two versions represent parallel realities that collided on July 14, 2015. Expected Pluto was a frozen, cratered relic like our Moon, geologically dead for billions of years, a time capsule with nothing to say. Actual Pluto is a living world with nitrogen glaciers that flow, mountains that grow, and an atmosphere that cycles with the seasons. Here is the counterintuitive comparison: Pluto is smaller than our Moon and receives 1,600 times less sunlight than Earth. It should be an ice ball. Yet it generates enough internal heat to drive active geology. It may not seem like much, but imagine this human-scale scenario: you walk into a freezer set to -400 degrees Fahrenheit expecting to find frozen food, and instead you find a pot of soup boiling on a stove. That is the scale of the shock. Pluto is warm enough to move. To understand the nitrogen ice tsunamis, we must define two commonly confused surface types on Pluto: active regions versus ancient terrains. Think of active regions, like Sputnik Planitia, as a lava lamp. The nitrogen ice is warm enough to circulate in slow convection cells, constantly resurfacing itself. There are zero impact craters here, the surface is less than 10 million years old, geologically newborn. Ancient terrains are the opposite: they are frozen graveyards, covered in craters from billions of years of bombardment. These regions are geologically dead and have been for eons. We can see the exact moment of transition in the imagery. The boundary between the heart, active, and the dark, cratered highlands, ancient, is a cliff, literally a wall where the flowing ice meets the frozen crust. The data shows this transition happened within the last few million years. Place this in context: 4 billion years ago, Pluto forms. 10 million years ago, Sputnik Planitia begins active convection. Today, the ice is still moving, still erasing its own history. So here is the core mystery, the miracle mechanism. How do you capture high-definition images of flowing glaciers during a 31,000 mile/hour flyby and transmit them across 3 billion miles with a radio transmitter that draws only 12 watts of power? For context, that is less than a single LED light bulb. The challenge is the signal delay. Here is the perspective ladder: light takes 1.3 seconds to reach the moon. Light takes 8 minutes to reach the sun. During the Pluto flyby, the signal took 4.5 hours to reach Earth. The signal obeys the inverse square law: it spreads out and weakens exponentially. By the time it arrives, it is barely distinguishable from background radiation. To catch it, we rely on NASA's Deep Space Network, 3 massive 70-meter dishes in California, Spain, and Australia. These receivers operate in continuous relay. As Earth rotates, one dish tracks the signal, then hands it off to the next. If the network goes offline, New Horizons screams into silence. The problem isn't the receiver on Earth, it's the dying power source aboard the probe. Solar panels are useless in the outer solar system. New Horizons runs on an RTG, a chunk of decaying plutonium-238 that converts radioactive heat into electricity. It launched with 245 watts of power. Today, it generates about 190 watts. Every year, we lose approximately 3.5 watts. We are already in emergency power rationing. We can no longer run the transmitter, the heaters, and the instruments at the same time. We must cycle them. We are approaching the emotional artifact, the moment when the final image of Pluto will be transmitted, and then the cameras will be shut off permanently to preserve power for the transmitter and critical systems. The Pluto flyby nearly didn't happen. The mission faced catastrophic failures in the final countdown. Just 10 days before the flyby, the main computer suffered a command overload and rebooted into safe mode. Contact was lost. Engineers had 72 hours to diagnose the fault, upload a patch, and reactivate the science instruments, or the entire flyby would have captured nothing but static. Then there was the data bottleneck. The probe collected 50 gigabits of data during the flyby, but the 12-watt transmitter could only send data at 1 to 4 kilobits per second. It took 15 months to download all the images. If the transmitter had failed during that window, the data would have been lost forever. And now, the future threat: as the RTG cools, the hydrazine fuel lines are at risk of freezing. If they freeze, the thrusters fail. If the thrusters fail, we cannot point the antenna. Engineers are now using waste heat from the electronics as emergency thermal blankets. The physics are unforgiving. Current projections give us until the mid to late 2040s, at most, 15 to 20 years remaining. The power curve cannot be reversed. The connection is finite. The silence is coming. Launched in 2006 with technology now considered ancient, New Horizons revealed that Pluto is not a frozen corpse, it is a living nightmare of nitrogen tsunamis and ice volcanoes. Even when the battery dies and the transmitter falls silent, the probe will continue its journey through the Kuiper Belt and beyond, a silent witness to the frozen world that refused to die.